Jnanam paramam dheyam. Knowledge is supreme.
So, now we are going to discuss the conditions in which a diatomic molecule, let us say, can absorb microwave radiation of the correct frequency. Okay. I started off writing selection rules, but then I remembered that there is something beyond selection rules as well. So, it is better to say conditions of microwave activity. Okay. You might know the conditions already, it is just that we are going to arrive at the conditions in a little more formal manner. Okay. And when we do that, we start from what we had written in the previous discussion. We start from your transition moment integral. Okay. What is the transition moment integral for a rigid rotor for transition from, say, J to J dash? Talking about J to J dash and M to M dash kind of transition. Is the problem clear what we are trying to do? We are saying that we are going to discuss a transition of a rigid rotor from quantum number Jm combination to a combination of quantum numbers J dash and M dash. Okay. What do I have to do? I have to write the integral. Now, while writing the integral, we have to remember something, it is not a simple integral, right. How many variables are there? 2, theta and phi. So, the integral has to be over theta as well as over phi. So, I do not know about you, but when I was your age, I used to get extremely scared whenever anybody wrote something like this. Like one integral is bad enough. So, if somebody writes 2 integrals one beside the other, then that would scare me, but I am sure you are braver and you are better in mathematics than what I used to be or I am. So, I hope this will not scare you. Okay. All I mean is that first we are going to integrate this, and then whatever we get, we integrate that with respect to the second variable, and we do not even have to do that. As you know, we are going to be able to write this as a product of 2 integrals. 2 integrals, 1 over theta, 1 over phi. I am going to write the limits soon. Okay. So, let us write this. Remember what transition moment integral is? Integral psi star mu psi, right, psi f star mu psi I. What is psi f star here? Well, I can write the normalization constants out already. Let us say I write the normalization condition normalization constant of the destination level as n dash, alright, n dash, then you have P J dash M dash in cos theta. Achha. Ideally I should have written P star, but as I hope you know, these polynomials in cos theta are actually all real. So, star does not arise here, but the next part, the phi part, what is the phi part? E to the power I m dash phi, is not it? But since I am writing it in the first one has to be complex conjugate, right. So, this I have to write the complex conjugate of it. What is the complex conjugate of e to the power I m dash phi? Minus, that is very simple, e to the power minus I m dash phi, right. What do I have to write next? I have to write the expression for mu, right. We will come back to this in a minute, mu. Then I write the initial wave function, that would be Pj mod m of cos theta e to the power I capital M phi. Now I do not have to write complex conjugate, right. The second wave function we write just itself multiplied by d tau. What did you tell me d tau was in the previous discussion? D tau is, Gurjot told us what? Sin theta, d theta, d phi, right? We do not worry about dr because r is not changing. Sin theta, d theta, d phi. Now let us write the limits. Since I have written sin theta first, second one will have limits of sin theta, theta, right? What are the limits of theta? 0 to pi or 2 pi? Pi. And what are the limits of phi? 0 to 2 pi, okay. And of course, I have to multiply it by the normalization constant of the first one as well. What I will do is the whole thing I will write maybe as a stylized normalization constant n, okay. Now, before proceeding any further, let me express it like this: n multiplied by, now see the two variables are independent of each other. So, I can write this double integral as a product of the integral in theta and integral in phi, right. Whatever is phi will become constant as far as theta is concerned and will come out of the integral. So, I can write it like this n multiplied by 0 to 2 pi e to the power, and I can simplify while writing this I m minus m dash but hold on, before I can do that I should know what I will write for mu, okay, what I will write for mu. Now, mu as you know is a vector sum of mu x plus mu y plus mu z, right, and you have told me in the previous discussion that mu z is equal to mu 0, okay, again I will write mu 0 here, mu 0 cos theta, this one is mu 0 sin theta sin phi, and this one is mu 0 sin theta cos phi, right. So, instead of this mu 0 I should write this sum, and the moment I write this sum it becomes apparent that I have to do it in 3 different steps. First I have to work with say mu x, then with mu y, then with mu z separately, okay. Since mu x and mu y are very similar, what I will do is I will work with mu z first. To start with, let us only consider this mu z. Now I can go ahead and I can write this. If I am working with only mu z, then what happens? I will write mu 0 cos theta, right. So, no component of phi here. So, as far as the first integral is concerned, it is complete. So, that comes in the second integral, which consists of your which is in terms of theta. Is this clear, or did I manage to confuse you in the last couple of minutes? I managed to confuse you in the last couple of minutes. Yes. Sorry, e raised to the power? Oh, right, phi is missing. Okay, good. If that is the case, then I did not confuse you in the last few minutes. Good. Are we clear so far? Can I go ahead? Before I go ahead, what is mu 0? That is a constant, isn't it? Doesn't depend on theta, doesn't depend on phi, doesn't depend well, does depend on r, but r is not changing. So, I can take mu 0 outside. So, I will write like this: n mu 0 integral 0 to 2 pi e to the power m minus m dash phi d phi integral cos theta multiplied by Well, I will write like this: P j dashed m dashed in cos theta multiplied by cos theta multiplied by P j mod m of cos theta multiplied by sin theta d theta. See if you have understood this. When we work with the z component of dipole moment, this is what my transition moment integral boils down to. Are we clear about that, or do we have any question? If you have a question, please ask now. Are we clear? Sure. So, first thing that we arrive at already before going any further is that if mu 0 equal to 0, then what happens? Then transition moment integral becomes 0 anyway, no matter what the other integrals are, and that means your molecule is not going to absorb any microwave radiation, irrespective of what is J, what is M. Okay? So, it turns out that a molecule has to be dipolar if it has to absorb any microwave radiation at all. Are we clear? So, which means that HCl is going to be microwave active, but H2 or Cl2 will not be microwave active. You need a permanent dipole moment for microwave activity. That is something that we arrive at right away before going any further. You knew this already, didn't you? Right? You knew this, but then this is how it comes. Any question? We will come to that. Right now we are working only with Z. We are going to talk about X and Z, Y also, but then see, no matter which component you take, instead of mu 0 cos theta, if I wrote mu 0 sin theta sin phi, mu 0 would still come out, right. So, even when we work with X component or Y component of dipole moment, this permanent dipole moment will turn out to be an essential condition. Okay, good question. Permanent dipole moment can be anywhere, right. Permanent dipole moment is along the direction it is. See, if you take HCl, you know what the direction is. I do not know whether HCl is along X or along Y or along Z or along something. Okay. For some position, you can resolve it into components for any position, okay, which will bring us to an important question in the next class. Okay. Any other question? Understood everybody? What have we obtained so far? Point number 1, a molecule must have a permanent dipole moment for it to be microwave active. That is something we have established. Now we are going to go to the selection rules. Okay. To do that, let us handle these two integrals separately. Let us call this phi integral in phi, let us call this I1, and let us call this integral in theta I2. Okay. May I erase the first line? Do not forget, as of now we are working only with the Z component of the dipole moment. Okay. What is I1? I am going to write this as delta M. Are you okay if you write this as delta M? M minus M dash delta M. It does not matter if you do not write. E to the power delta M phi d phi. What is that equal to? In fact, in order to work out this integral, we need to consider two different conditions. One in which delta M equal to 0 and one in which delta M is not equal to 0. Okay. What happens when delta M is equal to 0? What does this integral boil down to? Then it becomes integral 0 to 2 pi d phi, which is equal to 2 pi, which is not equal to 0, right. So, we see that the integral is non-zero if delta M is not equal to 0. Okay. So, delta M not equal to 0 turns out to be a selection rule when you work with mu z. Z component of dipole moment, right. So, we have already arrived at one selection rule which we may or may not have known earlier, okay. But as we will know, as we will see, this is not the only selection rule. Delta m can be something other than 0 when we talk about x component or y component of the dipole moment. Are we all clear? Sure? Okay. So, what we see is if delta m equal to 0, then the integral survives. What about the situation when delta m is non-zero? Then of course, this part is not valid anymore and you have to actually work this out. And to work this out, it is best if we switch over to the trigonometric form, okay. I hope we all know the trigonometric form. What is it? E to the power I k phi, or maybe I will write it directly, e to the power I delta m phi is equal to what? Cos delta m phi plus I sin delta m phi, alright. So, suppose I put this in here. So, this would be equal to integral 0 to 2 pi, this d phi will be integral 0 to 2 pi cos delta m phi d phi plus I integral 0 to 2 pi sin delta m phi yak. D phi. What is the integral in this case? Integral cos k phi d phi between limit 0 to 2 pi. 0 and 2 pi are the same points in space, isn't it? So, whatever is the value of cos phi will be the same, well, cos k phi. So, the first integral is 0, similarly second integral is also 0, okay. So, what we see is very important then, that in case of delta m equal to 0, transition takes place. In case of delta m equal to not equal to 0, transition cannot take place. That is a selection rule already, okay. When you work with the z component of the dipole moment, then it is essential that there should be no change in m, okay. If you want to think physically, what does it mean? What is m? Z component of angular momentum, okay. If you are working with mu z, right, that means actually, well, we will study this later, it means that you are working with the z component of the electric field that you are using, okay. Field is in this direction, angular momentum is also in this direction. Is there any reason why the angular momentum would turn? No, right. That is why delta m cannot be equal to 0 when you are working with mu z. More about this when we come to it from your time dependent perturbation theory. But let us now move on to I2. Are we okay with I1? Do we agree that delta m must be equal to must not be equal to 0? Yes. Sorry, must be equal to 0. What am I saying? Delta m must be equal to 0. Yeah. Of course. What he is saying is that we agree that using mu z, delta m has to be equal to 0. But can it still be non-zero using mu x and mu y? The answer is maybe yes. We will see to it. We will see. We do not know yet. But when we talk about mu z, definitely delta m has to be equal to 0 for the transition to have any chance. Okay. It is still going to be a disallowed transition if I2 is 0, alright. So, let us now see what I2 boils down to. Do not forget, we are working with the z component of the dipole moment. And since we are going to do work with I2 and we are already done with I1, instead of writing it once again, may I just erase everything other than I2? Great, thank you. this here is I2. Let me write this in a little simpler form. Let us say Z is cos theta. Okay. In that case, what is dz? Minus sin theta, d theta. Alright. So, see in I2 I can write this as p j dashed m dashed of z. Instead of this cos theta I can write z. Instead of this one I can write p j mod m of z. And what is sin theta d theta? That is minus dz, right. So, I can write it as dz, and I can just swap the limits, isn't it. Instead of 0 to pi, theta equal to 0 to pi, it becomes theta equal to pi to 0. Did I go too fast? Your question? Sorry? Minus sign? Okay, minus sign will come if I just write like this, theta equal to pi to theta equal to 0. Just switch the limits. Are we okay? Clear, Vikas? Okay. Now there is another Vikas in class. Yes. Sorry? Yes, so that is why I have written theta equal to pi and theta equal to 0. No, I will do that in the next step. But I thought that if I just write it right away, people might get confused. So, I will do it right now. So, when theta equal to pi, what is the value of z cos theta? Okay, let us do the easy one first. When theta equal to 0, what is z equal to cos theta? 1. And when theta equal to pi, what is z equal to cos theta? Minus 1 or plus 1? Sure? Huh? Okay, let me see. All sine tan cos, right? I remember this from my school days. All sine tan cos. So, it is minus 1. Minus 1 to plus 1. Do you agree with me that minus 1 to plus 1 for z, minus 1 to plus 1 covers all the possible values of z, right? Z is cos theta, right? Cannot be more than plus 1, cannot be less than minus 1. So, minus 1 to plus 1 for z is equivalent to minus infinity to plus infinity for a variable like say x Cartesian x. Are we clear with that? Maybe I should have written q so that you do not get confused. Anyway, now I have to evaluate this integral. To do that, I am going to use this recursion formula. See, I know already, isn't it? Z multiplied by pjm of z is equal to a1 multiplied by pj plus 1 m of z plus a2 multiplied by pj minus 1 m into z, sorry, not into z, of z. Okay, I can substitute it there. So, instead of this, I can write a1 p j plus 1 mod m of z plus a2 into p j minus 1 mod m into z. Agree or disagree? Do we agree or do we not agree? Strongly agree. Strongly agree is an option, you are right. Strongly agree is an option. Is there anybody who disagrees, or is there anybody who has not understood what we are trying to do? No? Sure? Okay. So, I will just write it like this. Alright. I can write it as a sum of two integrals now. It becomes a1 integral minus 1 to plus 1 p j dash. Now, instead of m dash, I might as well write just m, isn't it? Because we have already seen from the first from solution of I1 that m has to be equal to m dash, right, delta m must be 0, mod m of z p j mod m of z dz plus a2 integral minus 1 to plus 1 p j dash mod m of z multiplied by, what did I do? This is j plus 1, isn't it? P j minus 1 mod m of z dz. Maybe I should write it a little more neatly. I2 turns out to be a1 integral p j dash mod m of z between minus 1 to plus 1 multiplied by p j mod m of z dz plus integral minus 1 to plus 1 p j dash mod m of z multiplied by p j minus 1 mod m of z dz. Okay. Do we agree that this is I2? Okay. Now I ask you the question, these legendary polynomials are wave functions, right? So if I think of different legendary polynomials of the same set, will you agree with me that they form an orthonormal set, right? So a wave function multiplied by another wave function of the same set integrated over all space has to be equal to 0 if they are different, right, and has to be equal to, well, non-zero, ideally 1 if they are normalized, if they are same. Do you agree? Now, in that case, if you agree, tell me, when will this first integral survive? We have already discussed that this minus 1 to plus 1 limit is actually all space, right? When is this going to survive then? When will this survive? This will survive only when j dash equal to j plus 1. Is that right? And in that case, the second integral becomes 0. When will the second integral survive? Only when j dash equal to j minus 1. Is that right? This leads us to the condition that j dash must be equal to j plus minus 1 or delta j equal to plus minus 1. Is that right or is that right? It is right, and that is the selection rule that you are already familiar with. This is how it comes. Question, doubt, comment, nothing else? Sure? Yes. Yes. So, see, what I am trying to say is, if you are talking about mu z, then delta j equal to plus minus 1 is not the only selection rule. The other selection rule is delta m has to be equal to 0. So, it is actually a pair of selection rules, delta j equal to plus minus 1 and delta m equal to 0, and of course, mu 0 must be non-zero. These three together give you the condition for microwave activity if you are talking about the z component of the dipole moment.